take a minute. Okay. So any questions on what we've done so far? There were a couple of questions. I think there was a question on Academy on how to show the two fields of the same, choosing two different irreducible polynomials are isomorphic. I'll try to see if I can come up with a problem based on that in the first problem set, trying to understand fields a little more, or I will put access to some notes.
The reply of I just saw the reply of Ram Prasad. So it seemed like a very specific construction for that example, right? Like
yeah. So that was a very specific construction for that example. It's more involved to do it. You need a little more.
Okay.
See.
But it is known that you can find isomorphisms in polynomial time, but it's not immediate.
Okay.
It's actually a paper of Lenstra. Yeah.
Mm-hmm. Okay. Okay. Are there any other questions? Once here, we'll get started with the topic for today's. Okay. Let's get started. So the last two lectures we saw gave a series of applications to show the power of randomness. We saw how randomness was helpful in various computation contexts. We show that demonstrated examples where previously we did not have algorithms, and now using randomness we had algorithms. This one, and some cases where the algorithms were hard to obtain, but we knew of algorithms, but the corresponding randomized counterparts were much simpler and cleaner algorithms. So these all sort of show that randomness is a useful tool to have. It's a useful resource to use whenever one is trying to design algorithms or in other applications. What we'll today and for the focus of this lecture, is randomness actually needed in these applications? Randomness was a useful tool. We saw that, and there are whole sort of fields devoted to randomized algorithms and stuff. What we'll ask is randomness essential in this, or is it just sort of a meta object which we use and then can get rid of? So what do I mean? So the question we are going to ask today, and for the most part of this course, is randomness needed? And actually, I answered this question with the very first application that we saw. We gave an application for equality, where deterministically you needed to share n+1 bits if you wanted to solve it, whereas randomized you could do it with constant number of bits. So the answer to this question is certainly yes. There are problems for which we need randomness. So that's not going to be, if you just want an answer, is there a problem for which randomness is needed and there's no corresponding deterministic counterpart which does away, we can achieve the same performance? Yes, there are places where randomness is critical. It beats the corresponding deterministic counterparts. What we'll now ask, so you can't ask this on a universal level. So we'll ask this problem by problem, or for a class of problems. In these contexts, is randomness needed? And we'll see that this definition itself is going to take a while for us to build. What does it mean, randomness needed? This is going to be, to answer this question, it's going to take us a while, but let's start off with a toy example. Let's recall last time there was a question regarding the max cut example. Was it Arpan who had asked this?
Yes, sir. Yes.
Yeah. So let's go over that example, and what today we will see is randomness needed for that particular problem. So let's recall what max cut was. So the given problem was the input. The input is a graph. It's a simple graph, and the output is a cut. Yes, V minus S, that cuts as many edges as possible. So this was the problem in hand which we wanted to study. This was the max cut. This one, we mentioned that this is NP hard. This is not a problem that can be that we know how to solve. We don't expect to be able to solve this problem exactly. We won't be able to find the max cut. If you do this, that's a bigger problem we'll be trying to solve. What we showed last time was this following simple randomized algorithm. The algorithm was this. Output a random cut. Random set yes among all sets of 2 per b equivalently. So let's among all sets of vertices. What does that mean? More formally, I'm just going to be a bit pedantic about it. For each vertex b in v, add v let's toss a coin. I should have done this a little better. For each vertex I in n, so I'm going to call the set of vertices to be n. Toss coin ri. If ri equals 1, add vi to s, else don't. This is how we pick a random set. Pick a random set for each vertex, toss a coin, and based on the coin, decide whether you're going to put that vertex into the set or not the set. And an analysis we showed last time was the expected size of the cut S. Recall, this is exactly expected size over all possible edges. The indicator that yes cuts E, and this we saw was exactly this linearity of expectation. This quantity was half, therefore we got mod E by 2. So this was a randomized algorithm that on average managed to get that on an expectation managed to cut half the total number of edges. So there were 2 questions. One was Arpan last lecture, and actually one by Abhishek the previous lecture. Abhishek asked about how concentrated this is and stuff, and Arpan had a question about why, when you look at these 2 vertices, when you look at the pair of 2 endpoints of the vertex, why do you see all 4 possibilities? Arpan, now the way I stated it, it should be clear that you see all the 4 possibilities are equally likely.
Yes, sir.
Because this is how I pick a set. I pick a set by tossing a coin. Therefore, if I look with respect to the 2 endpoints of the vertices, I do see they are all 4 possibilities are equally likely. And in 2 of the 4 possibilities, the edge is going to be cut. The other 2 possibilities, the edge is not going to be cut. Okay?
Right.
And regarding, so that answers your question, but we'll actually come look at that a little more closely later in the lecture. And regarding Abhishek's question, he wanted to know concentration because what's the performance of this algorithm? First, let's stare at this algorithm a little bit and ask, is randomness needed for this algorithm? Can we get away with this randomness in this algorithm? And we'll see 3 different ways of trying to get rid of randomness in this algorithm. For this particular algorithm, some of them will be very general techniques. Some of them will be applicable in this context, and possibly we'll see in other contexts also. So we'll take this as a toy problem. Look at this. Let's look at this particular randomized algorithm, and let's see if you want to eliminate or reduce the amount of randomness needed for this algorithm, what needs to be done? That's the question which you're going to have. We just look at the focus of this particular algorithm and ask this. Now, what's one way to do it? We are showing that the question we're going to ask is, how can one eliminate or reduce randomness in the above algorithm? So the first technique which I'm going to talk about, technique 1, is going to be what I'm going to call enumeration. It's a very, very general technique. What do we know? You're tossed the coin and you're saying an expectation. What we could do is we could basically go over all possible settings of the coin. You're tossing n coins. We could basically, the thing is, just enumerate over all possible choice of the random coins. We know the number of choice of the random coins is polynomial because typically we're dealing with polynomial time algorithm. So is this a satisfactory answer? So that's the enumeration technique. So what would happen if I did this for the given problem? What happens? Is the thing clear? Just previously I said toss a coin. Now instead of tossing a coin, you go over all possible settings of a coin. How many settings of the coins are there? Is this thing clear? What I mean by this one, and what do I mean? So what do I mean by enumerate over all possible choices of the random coins? And is that clear what I mean by that? And if so, how many choices are there in this particular case?
2 to the power n.
2 to the power n, because every coin has 2 possibilities. There are n possible coins, therefore there are 2 to the n possibilities. So yes, you can, by going over all the 2 to the n possibilities, each of them you find the size of the cut, you can do it. Certainly you can, in this case, you can not only find that the average cut is this one, because you're going over all possible cuts, you can actually find the max cut. So this actually does eliminate randomness for all randomized algorithms, but it comes at a huge cost. It comes at a cost, you have to go over 2 per n times. So it does on the plus side, it does eliminate randomness indeed. But on the negative side, it's too expensive. Invariably, it's the number of choices is 2 power m, where m is the number of random coins tossed. So yeah, so this is a trivial way of getting randomness, but if m is usually like polynomial, as in this particular example, m was n, this is not a satisfactory answer at all. If m were really, really small, where m were like 10 or a log n or something, then of course 2 power m is still is not too bad a number. You can go over all possible choices. So in this case, this particular example, this is not a worthwhile technique. There will be places where this technique is actually useful, but right now, and this technique, notice this has nothing to do with this algorithm. It works for any algorithm. You can, as long as the number of coins is a particular choice of m, you can just go over all possible choices, which is 2 power m, and eliminate randomness completely. This is sort of math. This is not what I would have expected when I said I'm going to be eliminating randomness. We want more cleverer ways of doing this. But the reason I want to come back to this is because sometimes we'll observe the random. What we will try to do in algorithms is we won't be able to eliminate randomness. We will reduce the randomness from something to some other quantity. Say we manage to reduce the randomness needed by the algorithm from some huge polynomial to logarithmic. Then we can appeal to this technique, because now we can enumerate over all possible settings of the random coins. That's only polynomial, and then we can get rid of randomness completely. So we might see such examples. In fact, we will see one such example by the end of today's lecture. So that's the first technique. Any questions so far or comments? Next one, what is called the method of conditional expectations. So for this, let's focus on this one particular problem. Let's see how it works, and then we'll see if we can generalize it. Just like the enumeration method was not specific to the max cut problem. So what is it that we want? We are trying to, we show that over the random choices of the experiment, on average, we manage to get a cut that is exactly so, which cuts half the number of edges. Now, all I want to do is pick a cut. I don't care that on average I get a cut which picks it. If I manage to pick a cut that cuts half the number of edges, is good enough. So what we want to do is we're going to look at this. We're tossing n random points. The method of conditional expectation is going to be the following. In general, you're tossing n random points. And I know if I pick these random points at random, each one was a perfectly independent point toss, then the expected size of the cut is mod e by 2. Now, what you can do is, I toss the first coin. The first coin I asked. So previously, one way of eliminating, the previous way of eliminating was just go over all possible 2 power n choices. You could ask, for the first coin, is it good? Is it in my advantage for the coin to be tails or heads? Is it 0 or 1? Which is a better choice? Which way I'll cut this one? Once you decide that, then you can ask the next coin. Given that I chose a particular, made a particular decision for the first coin, what's the best choice for the second coin? You can now ask, is it better to make it heads or tails? And then, if you can find that out, say, suppose we are able to know whether it's better to choose heads or tails, we decide to make a choice and keep going. So what do I mean by this? So let's be a little more this one. So notice that we used R1, R2, Rn as the as random points. These are, so I'll sort of use a convention which Salil Vadan follows in his textbook. Capital letters typically will refer to random variables, and small letters will refer to instantiations of these random variables. So when I say R1, R2, Rn, this is a particular choice for the random variables. In this case, random coins, R1, R2, Rn. So what I want to ask is what? So we're going to ask this question. So suppose so we're going to ask this intermediate question. I have fixed some a priori, I have fixed first I coins. Suppose we have fixed the first I coins. To R1, R2, Ri. What is the best choice for the I plus first coin? Is it worthwhile to make it heads or tails? That's what I'm going to ask. So let's ask this question a little more. So I'm going to say, let's define this quantity E1, Ri is the expected value of the cut conditioned on the first coin being this, the second coin being this, and so on up to the Rith coin being Ri. So let's make this definition. So notice that E of when I given no things, this is exactly equal to expected value of the cut, which is we already calculated mod e by 2. This is just thing. Okay. And what is, and also let's notice what is R1 to Ri. By definition, this is just expected value over Ri plus 1 all the way up to Rn of R1 to Ri. I can also just write this as expected value of E of R1 to Ri plus 1. People okay with this so far? What I fixed the first Ri things. What's the this point? This expectation is this. people can either be completely comfortable with this or this might be completely new to people. So just ask me.
So I'm not able to follow. So you've defined R1 up to Ri as that quantity. That is fine.
Yeah.
And then, okay, so wait a second. I think even that is not fine. So what is S now? You have expectation.
Yes, S is something. S is a quantity determined by R1 to Rn. Once I tell you what are the random points, that determines the cut for us.
Okay, so S is the
By the way,
random.
so this itself is over the random choices of R1, R2, Rn. That all expectations are over the n random coins for us.
Mm-hmm.
But furthermore, I have conditioned that the first I coins are these specific values.
All right, so that I understand, and then
Okay.
you written note that E. What do you mean?
So note what did we show? We proved E of when I feed this nothing. I'm asking what's the expectation of cut yes when nothing has been set.
Okay.
So that's exactly what the expectation value we found out.
Yeah.
Okay.
So now the third line is.
The third line is I'm asking Ri, and I'm actually let's see, ignore this part for now. Just I want to say, so suppose I know the value, the expected value of the cut when I fix the first Ri, guys. I want to claim what is the first, when I know the first Ri plus 1, guys, it's exactly these guys. And depending on what choice for Ri plus 1 is, it's the probability, if it's Ri plus 1 is 0, this will take a particular value. So basically I want to claim this is exactly, so this is exactly ER1 to Ri 0. This happens with probability half because Ri plus 1 is half.
Yeah, okay. So it's like a martingale, right? You're developing a martingale.
Martingale is a linearity of expect what, yeah. It's
yeah. All right. So that's fine. Okay.
Yeah. So just this. Now my quantity is if in your experiment, if for example if your experiment, so what does this tell you? So I have a so once you have such a suppose these quantities, let's assume that this quantity was something you could compute. The algorithm could compute. If this particular algorithm for this max cut, it will turn out to be a quantity which I can compute, and we'll see that in a minute. But let's for now assume that I can compute this. Now I claim, suppose you can compute this, this will tell you how to eliminate the randomness, because I know to start off with, that's the E of this one. I know that's mod E by 2. Now suppose we have already made, so let's look at this. So because of this, I know that E of this one is E of 0 plus E of 1 by 2. That's the first experiment. That's just the instantiation of the above thing when I is 0. Now we know these three quantities. Suppose all of these three quantities were known to us. Now this certainly says this is mod E by 2. One of them has to be at least mod E by 2, because both of them can't be smaller than this is the average of these two quantities. So there's at least one of them which has to be larger than mod E by 2. You pick that one because you set the first point to be that way, and you keep doing this way. So each time you are at a particular choice, you have a particular expectation. This expectation is an average of two other expectations, and you pick that, and you know one of them has to be at least this quantity. So I want to say at each step.
So Prahladh,
yeah.
This question, I just got lost. So the thing is, so the initial expectation was over Ri plus 1 to Rn, and then where have
let me
Ri
just
plus
write
2
this.
to
Let me
Rn?
just write this. This we know is mod E by 2. Now, for I going from 1 to n, do the following. Let's compute E of R1, R2, Ri. So let's call 0 to n minus 1, 0, and compute this one too. Ri1, compute both of these quantities. I fixed at this step, in the ith step, I have already found out I minus 1, guys. I want to fit this one. If ER1 to Ri comma 0 is greater than or equal to ER1 to Ri, set Ri plus 1 to be equal to 0, else set Ri plus 1 to be equal to 1, and that's the end of loop. And output the S corresponding to R1, R2, R. Ishan, now does it answer your question? So suppose, so this is a quantity which we, so this is an expectation which I was able to compute, which we knew this. Suppose you are able to compute all these intermediate expectations also. These are what are called the conditional expectations. This is exactly what I mean by the conditional expectations. These are the conditional expectations. And what am I asking? So basically we are going through this process. We are initially with E. We are choosing a value such that ER1 is larger than or equal to this one. Then we are choosing a setting for R2 such that this is larger, and so on all the way up to the nth guy. And we know this is mod E by 2. Therefore, we would have found out a setting of the n coins such that it is larger than mod E by 2. Am I lost, people? Ask me questions. Ishan, what was your?
Yeah, no, I was just confused about, I think I still haven't got it. So, so maybe can you scroll up a bit?
Sure.
So we define the small e of R1 to Ri as this expectation over the coins I1, like Ri plus 1 to Rn.
Yes.
And then in the next step, we have the expectation.
This was the way we defined it. The green one is the way we defined it.
Okay.
Sorry,
Okay.
This was
right. Okay.
This is
So the first one is the definition, right? Yeah.
First one
Okay.
is the definition. Yeah. And it's not hard. I want to say this guy is. I want to claim that this you should be able to see. This is exactly this.
In the loop, if instead of greater than equal to, if you had a strict inequality, would the output be the best possible cut?
No, the point is the two values. Let's come to that later. But the answer is they might not be one. If you know the average of two quantities is at least this, it might not be. It might be the case that both of them are exactly the same. You might find no value which is greater than. You might not be able to proceed. I want to say at each step the loop you can proceed.
Okay.
How do you know that there is one greater than? All you know is there's one greater than or equal to.
No, that is true. You only know that it is greater than or equal to. But suppose there was a best cut.
Yeah, okay, you can do that. You can do that.
But you won't.
But there might not be. So it might be that at every step there's only equality.
No. There's something more deeper than that. So it could be the case that the like, for example, at the initial choice, when you decide to choose whether R1 equal to 0 or R1 equal to 1, it could be the case that when R1 equal to 0, the average size of the cut is really small. But the best cut could be among those. It's just swamped by many of the other cuts which are really, really bad.
Okay. Yeah.
So you are somehow you're taking a path down this tree guided by the average, and you might lose the best cut in the process.
Yeah. Okay.
Yeah. So basically, there is this one way of looking at it. There's this tree of cuts. Basically, you're choosing the first. Whether the first vertex or it has to go to the left side or the right side. Then the second vertex left side or right side. So there's this tree of depth n, which has 2 power n leaves, each of which correspond to a cut. And you basically, once you walk down this leaf, you are going to a cut, and that's going to be the value of the cut. And what each value at each intermediate node, let's put the average value of the cut of all its children. So you're having the average at the very top, and you're trying to walk, saying that at every node, its average value is the average of its 2 children. And so every node you have a particular average. You pick the better of the 2 and you walk along this cut. this need not pick you the max cut at the end of it. It will pick you a cut which is at least as large as E by 2. That's all you can guarantee. I cannot say I will go to the largest.
But maybe perhaps you can guarantee that you choose a max cut with a high probability by this procedure, perhaps.
Huh? It will be good if this one you can't show. I don't think it works. This algorithm doesn't give you anything better than half. You can show a little bit better than half. I think you can show you can get half plus 1 over n. You can get a 1 over n advantage.
Okay.
But that's it. This algorithm, I do not know how to get a better advantage of this.
So for a random graph, I think one should be able to show that this algorithm cannot. Suppose I develop a graph randomly and then I do this procedure.
Yeah.
Let's say g(n)half I'm using.
Yeah.
It seems that one should be able to show that this algorithm cannot.
This algorithm cannot do better. You will just be able to get a 1 over n. You can do by 1 over n, and that's this. You can show that this is the best you can do for the group. Okay. Okay. Where am I going with all of this? I just set up this method. I've assumed that we can compute these intermediate values. If I could compute these intermediate values, I would know how to set the random points. Previously, the enumeration technique went over all possible random points, but here we are sort of incrementally. I'm going to set the first random point in a favorable way, either 0 or 1, depending which one maximizes the conditional expectation. Then having fixed that, I'm asking the second point, which way should I fix it, 0 or 1, so that the next conditional expectation is also maximized. And you keep doing this. So I can do this experiment if I can come. The main thing is I need to be able to do this. I need to be able to compute these quantities to determine this. This particular example, let's actually see that we can compute these quantities. For this particular max cut example. By the way, this need not be expectations. It could also be a probability. You have an algorithm that with high probability gives you the right answer. Now you want to find out a choice of coin tosses. So you can pick the first probability you fix the first coin toss, and can you now ask this conditional probability also, can you compute? You know at least one of the two conditional probabilities. Each conditional probability is the average of the subsequent conditional probabilities. If you can do or compute these conditional probabilities, you can take exactly the same path which you are doing. You can just walk along this path tree and find a set of coins which will work at least as good as the original guarantee. So all of these algorithms depend on the fact that you can compute these conditional probabilities or conditional expectations efficiently along the way. This might not always be the case. For this particular case of the max cut, let's see if we can compute it. So is the setup clear so far? So question I want to ask now is, are the conditional expectations E of R1 to Ri easily computed? That's the question I want to ask. In this particular setting, we'll see that actually this is the case. So suppose I give you the coins R1 to Ri. These are fixed coins. So now let's look at, I'm at this particular set. What do we know about the graph? So there's this graph. So I want to claim already some vertices so are in the cut, are in SI. So let SI be, so I want to claim the entire set of vertices is divided into 3 parts. So I want to say V is going to be written as, at this point, I want to say as UI. And what is it? Yes, SI union TI is exactly the first I vertices. And it tell you what the cut, it's the corresponding cut determined by the random coins R1 to Ri, and UI is, I have no idea what those. So this is my partial information. At this point of time, I know SI is in the cut, TI is not in the cut, and UI are vertices whose cut value has not yet been determined. Okay. So
do you mean the union is R1 up to Ri, or do you mean?
R1 up to Ri for me refer to random points. I1 to I refer to the vertices. So once I set the vertices, these are the, this is the I'm saying, basically I'm going to say Si is a set of all, j less than or equal to I such that Rj is 0 or Rj is 1. It's the guys who I picked up in the cut. Ti is set of all j less than or equal to I such that Rj is 0 and Ui is exactly the remaining vertices. Okay. If I'm formal, that's what I mean. So the first I vertices, we have determined which side of the cut they are going. The left, if the random coin is 1, it's in the cut. If the random coin is 0, it's not in the cut. So Si and Ti have been determined. The remaining have not been determined. Now let's look at what is. Now I want to claim that this quantity E of R1 to Ri, you can of course write it, do it formally, but I want to claim that at this point of time, we actually know how we can write this. So certainly E of Ri is the expected value of the cut given the current choice. What will this be? Certainly it's going to include all the vertices between Si and Ti. And for every other edge, you have to find out what is the problem. What is it going to be in this side of the cut, or is it going to be the other? Is it going to be cut or not? Notice for every other edge, there's a half probability it will be cut and a half probability it will not be cut. This edge could be either an edge completely within Ui or having one point in Ui and another point in Si or Ti. Irrespective of that, there's exactly a half probability in which it's cut or not cut. So I want to claim this quantity is exactly half cut of Ui and the remaining, all the remaining vertices. Once again, linearity of expectation will give you this answer.
Could you explain this last thing? Why is it Ui and the rest of the vertices?
Why is it?
The Ui and the rest of the vertices.
So let's look at this. This was defined to be. Let's just E of let's just go with the definition. E1 Ri was the expected value of the cut of S conditioned on for all j less than or equal to I, Ri equals Ri. Exactly. Now, what is this? This is exactly by linearity of expectation. This is for all E. It's the expected value of the indicator that yes cuts E condition on for all j less than or equal to I, Ri equals Ri. Notice if E were an edge between Si and Ti, it's already been cut. So all of those guys are all going to come in this. There are various types of E's. If E is an edge between Si and Ti, it's called cut. If E is an edge fully in Si, it's not cut. If E is an edge fully in Ti, it's not cut. Now look at every other edge. An edge between, what are the other edges? All the other edges have one end, at least one endpoint in Ui. And each of them, there's exactly a probability of half that they will be cut. Take every edge over here. Let's look at one particular edge. Let's look at this edge. There's an edge of this sort. I want to claim what's the probability it will be cut. If this endpoint goes into S, you choose it to pick it into Si, it's going to be cut. If you choose it to pick it into Ti, it's not going to be cut. This one. If you choose it not to the cut. Therefore, for every other edge, for each of the edges going between Ui and all the remaining vertices, they get cut with probability half. People, is that answer your question? I didn't follow who asked.
Yes, sir. Yeah, thank you.
So this is the reason why this is exactly, I'm using the same linearity of expectation argument that we had used to calculate the original expectation. So each of these quantities actually you can compute along the way. That is, at every single step, this is a number you can cut. The cut between Ui and N, you can write it down. Give me R1, you can find out what Ui is. You can find what are the number of edges. This is the expectation. And all this algorithm is asking is this conditional expectation larger than this quantity? You check it out and then choose this path along the tree. So right now, all I have said is all of these. So because this quantity is something we can easily compute. I give you R1 to Rn, certainly you can find out this. You can also find out this. Therefore, this quantity is exactly this quantity plus half this quantity. So you know all the conditional expectations at every single step. And so you can keep doing this algorithm. People with me so far?
Prahladh, maybe I got lost here. So, okay, SITI, the cut SITI is basically all the edges going from SI to TI.
Yes.
And UI, comma N, this is talking about like edges where one vertex is still undecided in UI and the
other vertex could be anywhere.
Could be anywhere.
Yes.
And why is that cut with probability half?
Just take every choice of such an edge. So this edge could be both completely in UI, in which case there are 4 possible choices for the endpoint.
And then okay, makes sense. Yeah, right. Okay.
Do a case by case. There are 3 different cases you have to look at, and all 3 it's half.
It's half.
That's all. Okay. Is that fine? So you can compute this, but actually I want to say this algorithm is much simpler than what it looks like. So notice this is this just demonstrates that all the conditional expectations are easy to calculate. Let's actually be a little more careful. Let's look at R1 to Ri. This is what we actually needed to calculate, if you recall. Let's write 1 actually. What is this? Of course, I can write this down. I want to claim, if you write it a little carefully, this is exactly the cut between SI, TI. So let me draw the picture again. So you have SI, have TI, and now, sorry, they don't overlap. This is a long picture. This SI, this TI, and then this. Now you're going to determine the I plus first vertex where it's going to go, and then there's a remaining UI plus 1. So I plus 1, you're going to determine whether it's going. The coin, you're going to decide whether it's worthwhile to toss the coin heads or tails, whether to put the coin into the cut or outside the cut. So let's look at what happens. This will be this. And I want to claim this is exactly, now look at the edges going from I plus 1. This is exactly, you will cut them only with, so if I chose it to be in the cut, I would cut all the edges going from it to TI plus half cut UI plus 1. Yeah. Once again, the same linearity expectation. I'm looking at the different types of edges. I'm looking at the edges whose both endpoints are within SI and TI. Edges which have one endpoint in I plus 1, that is this guy. They will, out of them, which if I'm going to toss it heads, the cut, it will be cut only if I put it into T. If I put it in, this will be the number of edges I'll cut. Because I'm choosing it to be in the cut. And all the remaining things will get cut with probability half exactly. And similar, by exact similar argument, similarly, we can show that E of R1 Ri 0 is exactly size of cut of SI TI plus cut I plus 1 SI now, because if I'm going to put it 0, the number of edges you will be cutting is, it will be the number of edges going from I plus 1 to SI plus half cut UI plus 1. Yeah. This is okay. It's the same linearity of expectation argument. Look at it carefully. Look at all the different types of edges. Some edges are within SITI, some edges are going between I plus 1, and so on. Questions so far? And what did we want to pick? We wanted to pick the greater of the two. You know the average is a particular value. You're going to pick the one which is greater. Usually you pick the greater one and you choose the value of the cut. That's one way of choosing it. And the greater one, notice that two quantities, this quantity and this quantity are the same in both. Same as this and this is the same in both. The only thing that is different is this quantity versus this quantity. So all that you need to do at the I plus first point, with the I plus first vertex, you just need to determine, should I put it into the cut or out of the cut? So we need to find, so basically all I'm claiming is this quantity E R1 to Ri1 minus E R1 to Ri0. The difference between them is exactly cut I plus 1 Ti minus cut I plus 1. Yes, sir. So this algorithm at every step, so each time you have to pick you have to decide whether it's in your favor to put at the ith step, you need to decide whether you want to put the ith vertex in the cut or outside the cut. All that you need to determine are these two quantities. This quantity and this quantity. In the existing cut, are there more edges going inside or outside? And accordingly, in other words, the following algorithm is just the same, whatever the algorithm above is exactly the following algorithm. For I going from 0 to n minus 1, compute cut I plus 1 Ti and cut I plus 1 Si. If cut I plus 1 Ti is greater than or equal to cut I plus 1 Si, set Ri plus 1 to 1, else Ri plus 1 to 0. And that's also the same. This is just the greedy thing. The first vertex you determine arbitrarily. The next vertex you find out you have already determined the cut. You're just proceeding the cut incrementally. At each time you decide you already have a partial cut Si at Ti. So the way the algorithm proceeds is you have a partial cut Si and Ti already at some height step. Now the I plus first vertex comes. You're going to ask, do I want to put it here, or do I want to toss it here, or do I want to put it here? And you just determine which way are you going to cut more edges, and according to that, just put it in one of them and keep going. This simple greedy algorithm is the method is what you get by doing the method of conditional expectations on this randomized algorithm that we did. So these two are exactly the same algorithm.
Is T of 0 n or n minus 1 here?
Huh?
T of 0. So
T of 0 is n.
N.
Yeah. So there is no 0. The vertices are 1 to n. So T of 0 is everything.
T of 0 is also empty.
Sorry, T of 0 is empty. S of 0 is empty. So T of 0 and S of 0 are, if you recall, this is the definition. T of 0 is the cut that has been determined up to this point. So both are empty at this point.
In words, it's like Si is the set of vertices you have decided to put inside the final cut, the final set S. Ti is the set of vertices that have decided or not going to take. And UIs are the vertices that you haven't made up your mind yet.
Si, T0.
So cut of a set with respect to an empty set, what is the definition then?
Basically, it's also empty, because a definition of a cut edge is that one endpoint must be in your set and one endpoint must be outside.
Okay.
But this is vacuously
true.
Empty.
Okay. So this is just the greedy algorithm. So most cases, nobody discusses this algorithm to such gory details. They usually just give the greedy algorithm and show that it gets you half the value of the cut. The only reason we did this, we show that the randomization gives you, and if you de-randomize it using method of conditional expectations, what you get is actually this simple greedy algorithm. Okay, is this clear? So, but the method of conditional expectations is more, in this case, it turned out to trivialize into this very clean greedy algorithm. But method of conditional expectation is something a little more general than that. It says that if it's this general algorithm stretch, it says you can do this if all these quantities, if these quantities are computable at every step. It so happens in this case you can. There will be some problems for which you can't compute these intermediate conditional expectations, and so this method will not be applicable. In this case, it is applicable, and in fact, if you stare at this algorithm a little bit, this just turns out to be the greedy algorithm. Okay. Questions? Okay. So that's the first technique. This is a general technique. So after designing a randomized algorithm, one technique is to see if these intermediate conditional properties and conditional expectations are something you can compute. If you can compute, you can get rid of the randomness, because it tells you basically each incrementally how to toss the random coin. It tells you whether to pick it to be 0 or 1, 0 or 1, which way is the better choice. So you'll at least be as good as the average. You won't go to the maximum, but you'll be at least as good as the average if you keep doing this. So if all the intermediate conditional expectations are something you can compute for the specific problem that you have, then you can completely de-randomize the algorithm. As what happened in the case for MaxCut, you de-randomize the algorithm and you ended up with this greedy algorithm, the incremental greedy algorithm that one usually develops when one looks at MaxCut. Okay, questions? Okay.
Sir,
yeah.
Sir, I had a question. Initially we were specific about tossing a coin for each widgets and then proceeding, sir. So if we don't do that, and if we somehow guarantee that each S can be chosen equally likely, so even then the probability will be half, right? Like in the first step, which we did for the MaxCut, like the first step.
Yeah. So what's the but what's the question?
So even if we don't toss a coin and somehow ensure that the set S we choose is equally likely, each of the set S we choose, it's equally likely to occur, even then the probability will be half, right? Like an edge is a cut edge, the probability of that will be
half. Yes.
Oh.
So I don't follow. Going to be. I thought I had charged this, but anyway, let's.
Yeah, maybe to answer. Maybe
I didn't follow the question fully.
So I guess Arvind's question was that, suppose you had a completely different method of finally choosing your set S, which just guarantees that at the end of it, every set is equally likely. Then the expectation calculation of MaxCut will still give you like E/2. That is correct. But I guess the whole point of method of conditional expectation is that if you can somehow break down these choices into smaller and smaller choices in such a way that you can then choose the right path. So I guess it depends on how you are picking the set S eventually. In the example that Prahladh defined, I mean, like the set S was chosen in the most natural way, which is every vertex you tossed a coin, decided to put it in or not in. So you can mentally think of doing this halfway and then asking, okay, am I making a good choice or not? So I guess it depends on what particular process you have in mind.
Yeah, this is just asking how do you implement the fact of picking a random cut. This actually goes back to Arpan's question. What does it mean to picking a random cut? One way of implementing it is toss a coin for each vertex and decide to put it in the cut or not cut. And this particular way is what we de-randomized. There might be a different way. In fact, we will see another way to pick a random cut just right now. That's going to be the next third technique. We're going to pick a random cut. It won't be a random set, but it will be some other set. So we're going to use limited. Okay. So let's get on to the.
So, but suppose you have a way of getting, some way to construct subsets which are such that each subset is equally likely.
Yeah.
Then the probability distribution is the same as the original one, as the one you obtain by tossing random points.
If each subset is equally likely, if all the 2-power n subsets are equally likely, then this is exactly the same distribution. It's just another way of describing it.
Okay.
Yeah.
No, I guess, I mean, I'm not sure. Maybe Arvind can correct me if I'm misunderstanding his question. I guess Arvind's question was, suppose there was some choice of R1 through Rm, which at the end of it yielded a uniformly random set. Now, it may be the case that, by asking what happens if I have decided on R1, R2, R3, but the other choices I have not determined yet, it's unclear whether this may have a nice interpretable meaning. Like, I don't know if the analog of the function E that Prahladh had defined here, I mean, would you expect to calculate this efficiently?
So think of E, for this case, E, in general, the way I defined E was just a sequence of random points. The algorithm tosses a sequence of random points, and you are asking, if the first I coins were tossed this way, then what is the best way to choose the I plus first coin so that the average is still larger than each time the average only keeps, it doesn't decrease. This is something you can compute. One way of viewing these random points is actually the choice of the set yes over here. It could be a different one. This could be completely nothing to do with the set yes, but you could ask this question that if you're picking random points, you ask the corresponding conditional expectations for a particular problem and keep computing this. So in the max cut case, the random points and the set were very intimately related. In fact, the random points exactly told you what the set was. This might not always be the case. In that way, in those are the cases where this conditional expectation might not be easy to compute. So you'll see, I'll try to see if I can cook up a problem in which a conditional expectation based problem where it's not this obvious, the random coins and the choice of the set yes. We'll see if I can give such a problem in the problem set. Okay, fair. I'm already way behind time. So let's go to the next application, which is limited independence. So this will go back to one of the questions that was asked. Recall how did we calculate the expected value of the cut? Yes. This was exactly, we went over all edges ij in E, and this was exactly the probability that yes cuts ing. Yes cuts the edge ij. Equivalently, this is just in the language of random points. This is just the probability that Ri is not equal to Rj. To get half the number of edges, all that we wanted is for every pair I and j, this probability was half. This is all this the randomized algorithm. Now forget about the conditional expectation. Let's go back to the original random algorithm to show that this quantity, to show that this number, and then we concluded that this is mod e by 2. The only thing that we needed, the observation I'm going to make now is for above argument, we only need this is all that you need. That is for the following suffices of the random points. Following suffices. That is for all I not equal to j, probability Ri not equal to Rj was equal to half. If we had this, if there was some distribution of random points, so that for every pair of distinct coins, the probability that they were not equal was half, then the expected value of the cut is e by 2. This, notice that if you pick the coins independently, n independent coins, certainly you have this property. But that you don't need, what I'm claiming is that you don't need that huge independence property. You could do it with much fewer independence. You could possibly, I could choose the cut in such a way so that for every pair of coins, I could make sure that their probability that they are not equal is half. But for every triple, one way of making sure of this is for every pair, you see all possible 4 values. For every pair of coins, you see all the 4 possible values. But possibly for every triple of coins, you don't see all possible 8 values. Possibly that the third coin is exactly the third coin is a XOR of the first 2 coins. In this case, when you see a triple of coins, you won't see all possible 8 values. But the analysis which we used never needed to see triples. The analysis only cared of pairs. So as long as you picked n coins, so the only observation I want to make because of this, if you picked n coins, such that they were pairwise independent. That would have sufficed for us for this particular problem. You do not have to pick n completely independent coins. All that we want is hence I want to make this observation. This is observation 1. For the randomized algorithm, it suffices if R1 to Rn were pairwise independent. What do I mean by this? That is, for all ij, for all I not equal to j, the probability, why do I keep writing this? Ri equals some bi and rj equals some bj. This is equal to 1/4. That is for all bi, bj in 0, 1. For every such possibilities, I see this. This is all I care for. I don't need to know that all the n coins are completely independent. If I manage to pick a bunch of coins that this property is satisfied, that will still give me a cut whose expected value is mod e by 2. The analysis only requires this property. It doesn't require anything more of the random coins. Are people with me so far? So the question now we'll ask is, can pairwise independent n coins be generated using fewer bits of randomness? If they can, that will also satisfy this.
So just to be clear for myself, we also demand that these RIs are uniformly distributed on 0, 1.
Yeah, that comes because of the 1/4. So if you average this over the other coin, this will also force that
you mean each
feels...
coordinate, you mean? Abhishek, did you mean that, or do you mean overall?
Each coordinate, the R1, R1 is uniformly distributed to 0, 1, because just pairwise independence will not give you 1/4. So that's
No. So I have asked. This was what I have said. So yeah. So it's not just pairwise independent. I want this 1/4.
Yeah, okay.
Yeah. So basically, what is the true property? I want the marginal on every coordinate to be uniform and every pair to be pairwise uniform. Pairwise independent, and if I see this, that was enough for the analysis to go through. And question is, to generate such coins, can I do it in a better fashion? For example, suppose you want to pick 3 coins. Let's just start off with a trivial example. I want to pick 3 coins which are pairwise independent. One way is actually one way of tossing 3 coins is actually I can toss 3 separate coins, R1, R2, R3, and they would be pairwise independent. Certainly, every pair will be independent. But I could have also picked R1, R2, and set R3 to be just the XOR of R1, R2. Now, the 3 coins are not independent. The third coin is completely determined the first 2. In fact, any coin is determined by the other 2. But on the other hand, if you look at any particular pair, distinct pair, you will see all possible 4 values. Among the 3 coins, you won't see all 8 values. There are only 4 values. But for any pair, you will see all possible 4 values. Do people see that? This is a setting of, so this I pick, these 2 I pick independently. And then I set R3 to be this. This is a setting of 3 coins in which are pairwise independent. Okay, and we'll just generalize this example. So if I want to pick n coins, let's think of n itself as 2 power k minus 1. Let's assume that n is a 1 less than a prime power. What we will do is I will pick R1, R2, Rk to be independent random coins. Fully independent random coins. Then for each set of K, but a non-empty set, let's set Rs to be the XOR of all Ris I in S. So for every set, I come up with a coin which is indexed by the set, name of the set. And what is that random coin? It's just the XOR of the elements of the random coins corresponding to the elements in the set. But notice that by this definition, R of a singleton set will be exactly equal to Ri. Okay, let's see if you follow this definition. That's how I'm going to. I want to claim that this set, the claim I want to make, if Rs, so 0 phi not equal to S, subset of K, is a pairwise independent set of 2 power K minus 1 coins. More formally, like Abhishek's question, actually what I want to show is, in fact, for all S not equal to T, I want to say probability that Rs is equal to some bit A and RT is some bit B is equal to 1/4. For all S and for all AB, which are 2.
So this, I mean, essentially seems like this pairwise independent hash function kind of idea. Right?
We'll come to that. We'll come to that. We'll come to that. Just let's first check whether this. I want to ask whether this is true. And I just want to say this. So what do I need to do for every S and T? I want to say Rs. Just this is R of S into. Let me write this in this one fashion, and then it should be immediate why this is true. This is R of S into string XOR R of S minus T. R of T is R of S intersection T XOR with R of T minus S. People with this follow these identities. So there are 3 points. There are 3 points here. There is R of S intersection T, R of S. So I want to claim that if S is not equal, if S is not equal to T and both of them are non-empty and ST non-empty, then at least 2 of S intersection T, S, T and TS are non-empty. Also, R S intersection T or S minus T or T minus S are independent because they involve completely different set of coins. There is no, each of them involves a different set of coins and it's an XOR of a different set of coins. They are independent. Of course, one of them might be empty, in which case they are a fixed coin. It's just 0 all the time, but they are independent. These 3 things are independent. And now just stare at this. 3 of them, at least 2 of them are non-empty. So 2 of them are at least equally likely to be 0, 1. And RFS, RFT is an XOR of these guys. So they will continue to be independent. So this is just basically hence RS, RT are independent with the margin, with the uniform margin. People with me over here?
Yeah, so this is a great construction, but can you lower down the entropy of such a thing with log?
Look up the first problem set.
Oh, that's a problem.
Yeah.
So this is the best. You can't do.
No. We can do far better than this. We can do far better. We'll actually see another construction right away. This will not be good enough for some applications. Let's see what's the advantage of this construction already. Let's see what's the advantage of this construction. Let's see what's the advantage of this construction. So I want to claim. Let's look at what the particular case of. Let's look at for the particular case of the max cut. Now, can we use this example? We wanted to pick n coins, which were pairwise independent. So this tells you that think of n as 2 power k minus 1. If it's not, pick the largest case of that, smallest case of the 2 power k minus 1 is larger than or equal to n. I get more coins than necessary, which are pairwise independent. Who cares? As long as so you pick this number of coins. So you pick, so for a given setting, to actually get n pairwise independent coins, all that you needed were actually log of n plus 1. So in other words, the conclusion of this to say is to obtain n independent coins, n pairwise independent coins, one only needs log of n plus 1 independent coins. Let's call it, just to be granted, fully independent coins. So if your analysis of the performance of the randomized algorithm needed only pairwise independence, you do not need to pick up these coins independently. You can pick up these coins from a much more restricted space. For example, this tells you for the max cut example, you don't have to go over all possible sets, all possible 2 power n sets. It's only sufficient to choose n plus 1 log of n plus 1 vertices, and then the rest remaining are all set this way. Therefore, this will tell you that what's the number. So if now you apply the enumeration scheme, it will tell you there are only n plus 1 cuts you actually need to look at. You don't need to look at 2 power
what do you
n
mean
cuts.
by conclusion here? This is conclusion of what?
To obtain n pairwise independent points, one only needs so much. We don't need more than this.
No, but we haven't concluded this at all, right?
We have, no? This is the proof of this is that.
Oh, sorry. I misunderstood. Okay, yeah.
This claim, it's the conclusion of this claim.
Sure.
This claim tells you, so I pick only k independent points. Then I come up with RFS, 2 power k minus 1 coins, a much larger set. I just pick a small set of fully independent coins. From that, I break this 2 power n k minus 1 set of coins, define them this way. They are not fully independent. There's huge relationship there. If I know the first value of the first k, then everything else has been determined. So they are not independent coins, but yet they are pairwise independent. Every pair of them, you see the right marginal. You see the right. For every pair of them, you see all 4 values equally likely. And this is all we needed for the max cut exam. Are people with me? So for the max cut exam.
So I had a question.
Sure.
So you took XOR in this case.
Yeah.
I'm sure there are other functions that work as well, right?
There could be other functions. We are going to see just another example right away. We're going to see another example right away. Yeah. XOR is a very nice, with respect to these things, XOR is very nice. There are other examples, but XOR is very nice in this sense. Questions so far. So now, by the way, now if you apply this techniques and the enumeration technique, this shows that you don't have to go over all possible cuts. You don't have to go over all possible 2 power n cuts. it's sufficient to just go over n plus 1 cuts determined by these points. Average of them will the average of these cuts will be mod e by 2. Therefore, there will be certainly one of these cuts which is at least mod e by 2. Of course, none of these cuts might be the max cut. Max cut is possibly completely escapes this one. But you know at least one of these cuts, the average of these cuts is mod e by 2. Therefore, at least one of them is mod e by 2. So therefore, you have to go over only possible n plus 1 different cuts. Why do I get n plus 1? N plus 1 is 2 power log n plus 1. That's n plus 1. So if you go over n plus 1 cuts, apply the enumeration technique over these n plus 1 cuts. Rather, I'm applying the enumeration technique over the log n plus 1 fully independent choice of coin tosses. That means there are n plus 1 possible fully independent choices of the random coins. For each of them, you get a much larger number set of coins. Use the corresponding cut, and max cut can be de-randomized completely this way. I'm not writing down these steps, but it should be clear. That is, once I know how to reduce the amount of randomness needed, then you do the enumeration technique. Questions so far?
Yeah, so suppose now I try to use the previous conditional expectation method. It is not going to be the same easy thing, right?
It's not going to be. Yeah, it's not going to be.
So that average thing, we can't say the half of.
Yeah.
Okay.
So the conditional expectations is, you might still be able to compute it. In this case, I think you can still compute it, but it's not as easy as the task as what I had said. So there will be cases in which actually, depending on how you are using the random coins, the conditional expectations might not be easily calculatable at all in the first. Okay. Questions on this? So this is one way of generating the pairwise independent coin tosses. We'll now ask, this is a very useful tool to have. So we'll see if there's a much nicer way of generating this. So we're going to ask a slightly more, I'm going to spend some time. This is what Varun asked. I have about 10 minutes and
the way to compute the E function is to consider the first log n plus 1 vertices as the ones which you had the independent tosses, right? Or is that the way you are thinking about computing the small e function here?
Yeah. So there you will have to R1, R2, Rs. You're going the conditional expectations. Notice that you will do the same thing, but the point is, it's not hard to do it. You can once you.
I mean, after log n plus 1 steps, it's deterministic, right?
After log n plus 1 steps is determined, but various other values, you'll have to be a little careful by how we use this fact that for every edge, it's equally likely that cut values are this one. You need to be careful about this calculation. It can be done. I don't think it's not. I don't think it's
no. Even the definition of E R1 through Ri seems unclear. Does I refer to the number of vertices, or does I refer to the number of independent coin tosses that you have decided already?
So let's make an appropriate definition. Let's make the way I defined it was the independent coin tosses. So you can ask, given this first I coins, which is, you can think of them as determining the first I. In this case, it's easy. It just determines the first I vertices. First log n plus 1 vertices, you determine which side of the cut to go. That determines for all the remaining vertices which side of the cut they are going to go into. You could think of this algorithm going this way. There are various ways to do it.
Let's take this offline. I think it's trickier than that.
Yeah, it requires work, but it's not hard. That's all I want to say. In this step also, you can compute it this way. You can go this way. I don't see the advantage of doing it, but you can do it. Calculation. But let's go to this one. Now, what did we have? I wanted n random coins. The question was, we needed n random coins. N random coins which were pairwise independent, and we show how to do this. Let's ask a slightly more general question. I don't want n random coins, but I want sometimes I want not coins, but actually want n random strings. So I want n random strings. So So rather, let's call it n random elements. So each in the range m. Previously, m was just had two choices, 0 and 1, but now possibly m is. So I want n coins, to each of which. So basically, this is the choice. I want n coins. There are n of them, and each of them independent. Each of them is equally likely. Each of them is uniform in the set m. So suppose this was the property I want. I wanted n coins this way. Each of them is the marginal
n
on
samples. Yeah.
I want n samples or n random elements. Each of them is uniform in 1 to m, and every pair of them is independent. But I don't care about any further correlations. How can I do this? How can I generate this sequence of samples? Is the question clear? So, want to generate n random samples. Let's call it, say, R1, R2, Rn, such that I want two properties to be true. For all I, probability of Ri is equal to A for all I and for all A in M. This is exactly equal to 1 over M. I get this one. And furthermore, for all I not equal to J, and for all A, B in M. But let me just say this. Once I've said this, for all not equal to Ri and Rj are independent. Okay. So that's the goal. Let's see if we can construct this. Is the problem clear? Okay. Moving on a much slower pace than I wanted to, but that's fine. One way to do this is do the same. So you can think of M itself as 0, 1 to the M. So this, and I could just do the above process M times, and I would get this. I do it once to generate the first of the M bits. I do it another time to generate the second of the M bits. The third time, M times I do the above process, the previous process, and I would be able to generate this. So let's think of this as, just repeat the above XOR process M times. That will give you this one. So that recall that the total number of truly independent random coins needed is how much? I require M. I'm doing M this once, and furthermore, each one of them was log of n plus 1. So this is roughly like log M times log of n plus 1. That's the number of random coins. That example, the way of it would have worked. This is okay. Notice that if I want to now apply the enumeration technique on this number needs to be logarithmic in the input size. This is logarithmic if M were a constant. If M is not a constant, this is not logarithmic in the input size, like log square or some such thing. Now, we want a better construction than this. I don't want to apply the random experiment, the previous random XOR experiment, just independently small m times. We can do that also in a correlative fashion. Okay. People with me so far? So I'm now going to Okay, so spent a lot of time on finite fields last time. This is going to be one application of the finite fields. This one. So think of the following experiment. Consider the following experiment. So let FQ be a finite field of size Q. And I'm going to think of N as equal to Q. Therefore, I'm going to choose a finite field which is larger than the number of samples I take, and also I want M to be also Q. So think of so let's think of Q to be larger than or equal to max of both M and N. Both M and N. Q to be some number which is N. And how am I going to pick this sequence of samples? I'll just pick A and B. So this is the random experiment. So I'm going to generate samples R1, R2, or all the way up to Q, where Q is, well, these are the, this is now, let me not write it this way, should have been more careful. So let's look at the following experiment. I pick A and B at random from the field FQ, and for all alpha in FQ, I set R of alpha to be the string A alpha plus B. That's what I'm going. And I want to claim, the claim I want to make is, if I look at these strings, R of alpha, alpha in FQ, over random choice of AB. So AB is completely random in FQ cross FQ. This is pairwise independent. In fact, I want to say the following. In fact, for all CD in FQ cross FQ and alpha not equal to beta in FQ, we have the following. Write it over here. Probability for the random choice of AB, R alpha equals C and R beta equals D is exactly 1 over the size of the fields. So R alpha is going to take an element of the field.
So Prahladh, what do you mean by you want Q larger than this thing? I mean,
I have the requirement was M and N. Just choose a field whose size is larger than.
yeah, but this will not solve the problem we wanted. The thing, right? I mean, like here, these R alphas don't even fall in the range that you want.
I will later on. I will show how to. I haven't yet claimed this one. From this, we will do some trimming. I need to trim it down to knock off extra coins or bits and stuff to get it. But this will satisfy my. So I don't have time to do that. I'll possibly do that in the next lecture, or we'll go to the homework. So this is what I want. I'm already past 2 minutes, but let me quickly finish. This is what I want to claim. The proof of this is almost. So what's the probability we're asking? What's the probability over AB that A alpha plus beta equals C and A alpha plus B equals C and A beta plus B equals D. Notice this is exactly the probability I want to write down. A minus how do I write this? A alpha minus beta equals C minus D, and A alpha plus B equals C. And notice this is the probability of this happening is just this probability. Let's write it in a separate fashion again. How do I want to write this? Probability that A is equal to C minus D by M alpha minus beta times, that's probability over B, that B equals C minus A alpha conditioned on K equals C minus D by alpha minus beta. This is exactly 1 over the field size. This is also 1 over the field size. Okay, so what I want to just say, what is happening over here? So what's happening over here, think of the field. This picture, think of, this is FQ. Think of a plane like this, FQ. Think of the plane FQ cross FQ, this one. And when I pick A and B, what am I doing? I'm picking a random line. AB, I'm picking a random line. The line is given by y equals AX plus B. And each point over here corresponds, each R alpha is a point on the line. Each R alpha is A alpha plus beta, A alpha plus B. It corresponds to the point alpha comma A alpha plus B. So this point is alpha comma A alpha plus B. And corresponding to every point on the line is a random choice. The point is A alpha plus B. And I want to claim that these are pairwise independent. Notice once I know 2 of the points on the line, the third point is determined. These are once again, there's huge correlation of, they are not fully independent, but yet every pair of them are equally likely. That's all I want to claim here. We need to stare at this one. It's a very trivial, it's easy example once you're comfortable with fields, but on the other hand, it's a very profound example, very profound application of pairwise independence using finite fields. We'll come to this, but stare at this for a while before we meet on Thursday. I'll stop with this.
So should I take the stream offline?
Okay, let's ask any questions first and then.
This method can be generalized for M-wise independent instead of A alpha plus B, we can consider more.
So how would you do that?
Would it be summation AI alpha to the power I? I don't know. My guess is that you should go.
That exactly works. So this was a line. That's why I drew that picture. You choose A and B were determining a line. Now you determine if you want k-wise independence, you choose the coefficients of a degree k-1 polynomial at random, and then output the evaluations of this polynomial at various locations. Those will be k-wise independent. This just follows from the fact that a degree k-1 polynomial, if you care about k-wise independence, its value at k places are completely independent. They have no correlation with each other. Of course, once you know k places, the k plus first place is purely determined by interpolation, but every k places are completely independent. So this example, this just sort of extends to not just getting pairwise independence, it extends to getting any k-wise independent. You just don't choose, here you choose the coefficients of a linear polynomial, a degree 1 polynomial. That's because you wanted pairwise independent. If you want k-wise independent, you will choose the coefficients of a degree k-1 polynomial, and that will give you k-wise independence. Exact same constructions and exact same proof will tell you that. Yeah, so that's, in fact, that's the way typically people to pick up k-wise independent. I was planning to give this as a homework. Now that's off. No problem. Yeah. Any other questions?
So as in just as a curiosity, suppose I have a hypergraph on n vertices.
Yeah.
And each edge of the hypergraph just tells me that the corresponding vertices are independent.
Mm-hmm.
Is it known how to construct such a, random variable satisfies this constraint?
So it's the same thing. You suppose you want a hypergraph and you want to cut the hypergraph.
No, I don't want to cut the hypergraph. So
the hypergraph is telling you the independence requirements.
The independence requirement. No. So you are asking hypergraph. Okay. Sorry. I forgot.
So did I understand your question correctly, Abhishek?
Yes, absolutely. So here we have a complete uniform hypergraph of size 2. So we have a complete.
So here we have given the n points and you have the complete graph on.
Yes.
This one. Now we are asking. Suppose then Shubhada's thing was n things in which each hyperedge was set of size k.
Right.
And you had a complete k uniform hypergraph.
Right.
Now your question is, suppose I didn't care about the complete k uniform hypergraph. My problem only required these dependencies. Can I generate it in specific way? No, I haven't seen this generality how to do this.
All right.
So of course you pick if your hypergraph is k uniform, if you had solved the complete k uniform hypergraph problem, that will also satisfy this, but that's an overkill. If you knew that every edge had arity at most, every hyperedge had arity at most k, then Shubhada's construction for k-wise uniform will satisfy it, but it's more things are k-wise independent than what you need. So I don't know in this generality how to. Actually, I haven't seen this at all. It's a very nice problem. I haven't seen this. You give me the limited dependency structure, and if you want, then you get the thing that solves exactly that.
Yeah, and entropy questions one can ask. What is the best?
Yeah, so there's an entropy question about this. So we don't fully understand how many bits are needed for this. I'll give you some bounds, lower bounds for this. We will see in the problem set. We fully don't understand for limited wise independence how many bits are actually needed. Okay. It's satisfactory the most part, but we haven't yet pinned it down completely that both the upper and lower bounds don't exactly match yet. Okay. Any other questions?
I just wanted to ask, you had mentioned some resource on fields that you were going to link.
Yeah. I was planning to put it up, except that I could not find a PDF file. I only found a PS file, but I'll put it up anyway. Because this file was written in the late 90s. But I'll put a postscript or I'll convert it and post it up. Yeah, I'll look this up, yes. Yeah, we can stop the stream.
Okay.
Okay then. Okay.
Okay, see you all. So I'll end the meeting.